My slide is called rotation in R2, so rotation on the plane. So here's a map which I'm going to discuss here. It's a map which takes elements of R2 in R2. I mean in R2 to R2. And it does it like so. It's a map which, I mean the T of x, it's a vector of rotation of the vector x around the origin by a fixed angle alpha counterclockwise. It's the first time when the map, I mean, it's certainly a map, right? Every vector is signed another vector. You just take a vector, you rotate by angle alpha, and you end up with another vector. It is a map. It just, the first interesting thing about this map is that it's the map which is not given by a formula yet. It's described in the plain English. In fact, it's not just one map, it's many maps, right? For different alphas, it will be different map. So actually, I probably should reflect this dependence on alpha in the notations, and probably I will. So let me just call this, in order to reflect this dependence, I call this not T, I call it T of T sub alpha. To reflect that for different alpha angles, it will be different map. T sub alpha. I claim that this is a linear map. If you rotate something, it is a linear map. Geometrically, I have a diagram here which shows this. I have this diagram which I color-coded a little bit. So you see, here's my x vector, which was purple, and if you rotate this vector by this angle counterclockwise, here's the result of here's the result of this rotation. Here's the result of this rotation, T of x. Here's another vector y, which I call it blue, and here's the same angle, you see, by blue arc, and here's the result of this rotation, T of y, which is also blue. The red vector, it's a sum of x plus y. It's a parallelogram rule, as you can see. And the red vector here, as the result of the rotation, is the same arc, the same angle, T of x plus T of y. So this diagram shows you that it looks like that I'm not saying it's a proof yet. It's not a proof, of course. You can't prove things with a diagram like this. But it's an indication, positive indication, that the first property of the linear map should be satisfied for the rotations. And here's the indication that if you scale things, the second property of the linear map will be justified by the rotation. If this is a scaling, it's a green vector. It's a scale x vector by some scalar lambda. Here's a rotation of that, lambda T of x. So the diagram actually suggests that the rotation is a linear map. But if you want to prove this formally, we have to do something about it. And normally, I will do it like this. I will suggest, rather than just trying to figure out why by the rotation by the angle alpha is the linear map, I will suggest a linear map instead. And I will prove that this suggestion is exactly the rotation by the angle alpha. So I do it the other way around. Rather than trying to figure out that the rotation is a linear map, I do the other way. I'll make a suggestion of a linear map, and then I'll show that this linear map is rotation. Here's my suggestion. I need to reflect the dependence of alpha here. I will do it in a second. Here's my suggestion. For the vector x in R2, I suggest the linear map like this. You see, it's a two-dimensional vector with components. That's the first component, x1 cos alpha take x2 sine alpha. Here's the second component, x1 sine alpha, x2 plus x2 cos alpha. And actually, this is a linear map straight away if I make a reference to what we discussed on the slide before, because this one simply the product of the matrix A and the vector x, where x is this vector, and the matrix A is this vector, cos alpha negative sine alpha, cos alpha. So let me just reflect the dependence on alpha here. And strictly speaking, I have to reflect the dependence in the A matrix as well, but probably I will leave it out. So here we go. I suggest to take this map, which we know it's a linear map. We know it because I make a reference to the lemma I have just proved on my slide before. So this is a linear map. And I claim that this will be the map, that exactly will be the rotation by the angle alpha counterclockwise. How are we going to see that? Here we go. First, we just compute the length of the image. The length of the image vector, well, we all know how to compute the length on the modulus of the vector. It's sum of the squares of the components. Here's my components. x1 cos alpha, take x2 sine alpha square plus x1 sine alpha plus x2 cos alpha square. Here's the expansion. It's a binomial formula applied twice. Here's my expansion. Look at this. x1 square cos alpha square. It's the square of the first term here. Double product of these two terms, double x1, x2 cos alpha sine alpha, and then the square of the second term, x2 square sine square alpha. This is the expansion of the first binomial. Second binomial, here's the expansion. x1 square sine alpha square, double product, double x1, x2 sine alpha cos alpha. And the last square, x2 square cos square alpha. Is an expansion, rather lengthy one, but we see lots of simplifications here, right? Double products, they will cancel each other. Minus and plus, they counteract against each other. These two, we can refer to the fundamental relation between cos and sine. Here it is, sine square alpha plus cos square alpha always deliver 1. So these two, and these two, and these two, and these two deliver x1 square plus x2 square, which we know the modulus of the rex vector. So what do we see? We see that my linear map possesses the property that the image, or the length of the image, if you take the square root of this identity, I mean, if you take the square root of the left-hand side and square root of the right-hand side, you see that the modulus of the image, the same as the modulus of the original vector x. This is nice. It's already good. In fact, well, some of you will learn, some of you who will continue the study of mathematics later, you will learn that the maps which possess this property, they preserve the lengths of the vectors, and that's a typical example of the map which preserve the lengths of the vectors. Such maps, they call isometries. So this identity alone means that T is isometry.